Hello students, in today's lecture we are going to learn about waves. In this lecture we will cover NCERT section 14.3 to 14.3.1. This is our disclaimer. Learning objectives. By the end of this lecture you will be able to understand the mathematical representation of progressive waves through displacement relations and define or explain amplitude and phase of a progressive wave. Alright. So, in today's lecture, we will cover first 14.3 displacement relation in a progressive wave. Then 14.3.1 amplitude and phase. Let's understand the motion of a progressive wave. Alright. So, let's start by defining a progressive or traveling wave. This type of wave moves from one point in medium to another, carrying energy along with it. Look at figure. The wave shape shifts position over time. This movement is what makes it progressive. Emphasize that wave itself travels, not the medium as a whole. Alright, where on y-axis displacement, on horizontal axis equilibrium position. The main thing of a progressive wave is to transfer energy and momentum from one place to another within the medium. For example, when you shout across a field, the sound wave carries energy from your mouth to someone else's ear. The particles in the medium pass on this energy, allowing the wave to move forward. It's important to realize that the individual particles of the medium don't travel with the wave. Instead, they vibrate or oscillate back and forth around their original position. Or we can say, individual particles of the medium vibrate or oscillate about their equilibrium positions. Amplitude of the wave remains constant as it propagates through the medium. Alright. Now let's understand how we can describe a harmonic motion using mathematics. Now take a look at the diagram shown here, figure 14.3. This is a sinusoidal wave traveling along a stressed string. This one, sinusoidal wave. The repeating up and down pattern, that's what we call a harmonic or sinusoidal wave. The peaks and troughs show how the strings moves as the wave passes through. This one is vertical axis and horizontal axis. To represent the wave shown, function must be sinusoidal. That means it should have the same shape as a sine or cosine curve, which repeats in a regular pattern. Sinusoidal functions are perfect for describing waves because they naturally repeat. We need a function of both position x and time t. This is because the wave changes not just as you move along the string but also as time passes. So the function should tell us the displacement at any position x and at any time t. At every specific location on the string, the function should describe how the particle at that point moves up and down over time. In other words, it tells us the motion of each tiny bit of the string as the wave passes by. One last important thing is we focus on transverse waves, where the particles moves perpendicular to the direction the wave travels. I hope this is clear. Let's now understand displacement equations of wave motion. Let's look at the main equation for a progressive wave. Y of x t is equal to a sine kx minus omega t plus phi. This equation tells us how the displacement y of a point on the wave changes with both position x and time t. Alright, the sine function, which means the wave repeats in a regular, or we can say in a oscillating pattern, where y is displacement of the wave, alright, from the equilibrium position. X represents the position of the constituents of the medium. In other words, x tells us where along the wave we are measuring the displacement. The symbol A stands for the amplitude of the wave. Amplitude is the maximum displacement from the equilibrium position, and it tells us how tall the wave is. Now, k is called the angular wave number. It tells us how many wave cycles fit into a certain distance. Omega, written as the Greek letter, is the angular frequency, and phi is the initial phase of the wave. This determines where the wave starts at time t equal to 0 and position x is equal to 0. Alright, changing phi shifts the whole wave left or right. Now, here we see the general displacement equation for a wave, that is y of x t is equal to a sine kx minus omega t plus phi. Alright. So, using trigonometry identity, that is sine a plus b, or we can say sine a minus b, is equal to sine a cos b plus minus cos a sine b. This identity helps us break down the sign of a sum or a difference into simpler parts. Simplifying a wave equation as per given trigonometry formula. So y of x t is equal to a sine kx minus omega t cos phi plus cos kx minus omega t sine phi. We have separated the phase phi from the rest of the terms. So let's rearrange the terms. So y of x t is equal to sine kx minus omega t a cos phi plus cos kx minus omega t a sine phi. This makes it clear that the displacement is a combination of two separate wave components, each multiplied by a different constant. If we let a equal to a cos phi and b equal to a sine phi, we can write the equation as y of x t is equal to a sine kx minus omega t plus b cos kx minus omega t. Clear? It's a very general way to express a wave, and it shows that a wave can be written as a sum of sine and cosine terms with appropriate coefficients. Now we have equations as y x of t is equal to a sine kx minus omega t plus b cos kx minus omega t. Constants a and b are related to the amplitude a and phase phi as a equal to under root a square plus b square. Amplitude is the maximum displacement from the rest position and it's always a positive value. Clear? So we can say the small a is always a positive quantity. And phase phi is equal to tan inverse b by a. The phase phi tells us where the wave starts at time 0 or its initial angle. Changing the phase shifts the wave left or right along the x-axis. Clear? Now let's understand how a wave looks in space. We are going to focus on the shape of a traveling wave at a specific moment in time. So now let's take a fixed instant in time, say t equal to t naught. At this moment, the wave equation y of xt is equal to a sine kx minus omega t plus phi become y xt is equal to a sine kx plus constant. Clear? So the equation becomes this one. Here, small a is the amplitude which tells us the maximum displacement, and omega is the angular frequency. So at a fixed time, the wave shape depends on only on x. At this fixed instant, if we look at how y changes with x, so we see that the wave forms a sine wave along the x-axis. This means the shape of the wave in space at any given moment is a repeating pattern of peaks and troughs. So now take a fixed location, say x is equal to x naught. Then the sine function become y of xt is equal to a sine constant minus omega t. Clear? Let's examine how waves move through a medium. At any fixed point, the displacement of a particle changes in a smooth repeating way over time. Specifically, it follows a sinusoidal pattern. This means if you watch a single point like a cork floating on water, it moves up and down in a regular wave like motion. So every individual particles of the medium execute simple harmonic motion or SHM as wave propagates through it. Simple harmonic motion is a type of repetitive back and forth movement, like a mass on a spring or a pendulum swinging. Each particle does not travel with the wave, but instead oscillates around its own position. So let's look at how we describe these simple harmonic motions mathematically. So figure cosine and sine wave. We use sine and cosine functions to represent the displacement of each particle over time. In the figure, you can see both a sine wave, the red one, and the cosine wave, the black one. These are just two ways to show the same type of oscillation starting at different points. Now let's understand how to determine the direction in which a wave travels. So from the displacement equation of wave, y of xt is equal to a sine kx minus omega t plus phi. As t increases, x must increase in the positive direction to keep kx minus omega t plus phi constant. Thus, above equation 14.2 represents a sinusoidal harmonic wave traveling along the positive x direction. Remember, the sign in front of omega t is key. A minus sign means the wave moves in the positive x direction. So, what happens if the sign in the equation changes? If we have a plus sign instead, the wave travels in the negative x direction. That this is important because it tells us how to read the direction of the wave motion directly from the equation. So equation is y of x t is equal to a sine kx plus omega t plus phi. Since t increases to keep kx plus omega t plus phi constant, x must increase in negative direction. So always check the sign in front of omega t to determine which way the wave is traveling. Crest and trough. These are two terms you will need to understand as we study how wave moves and carry energy. So now let's focus on the crest. Alright, the crest is the highest point of the wave above its rest position. Imagine a water wave. The crest is the very top of the wave as it rises up. Clear? So the crest stands out as the maximum upward displacement. This is where the energy of the wave is at its peak in the upward direction. The trough is the lowest point of the wave or the maximum downward displacement from the rest position. It's the opposite of the crest. In the figure, crest and trough, you can see the trough at the bottom of the wave. Clear? Bottom of the wave. So these are the troughs. So every wave has both crests and troughs, and together they show us how the wave moves above and below its rest position. Clear? Now we will look at how a wave moves or progresses over time. Progression of a harmonic wave along the positive direction of the x-axis over different instants of time. So the point of maximum positive displacement on the wave, which is marked by a cross, or we can say cross symbol. Clear? So displacement means how far a point on the wave is from its rest position, and maximum positive displacement is the highest point above the center line. Clear? Above the center line, the maximum displacement here A. Take a look at the figure 14.6a to see where this cross is placed. This one. So finally, observe that a particle at the origin of the x-axis is shown by a solid dot. Clear? This one on our x-axis. The origin is the starting point or the position on our x-axis. This helps us track how the wave moves relative to a fixed point. Now, here we see a diagram showing a wave moving to the right along the positive x-axis. The sinusoidal shape, which is typically for many wave like sound or light. So in diagram A, 14.6a, we see the wave at its starting position at a specific moment in a time. The crest is marked with a cross showing exactly where it is along the x-axis. This helps us set a reference point to see how the wave changes as time passes. And let's look at diagram B, 14.6b. After some time has passed, the entire wave, including the marked crest, has shifted to the right. This shift shows us that the wave is propagating or moving along x-axis. So crest has shifted to the right along the positive x-axis, showing the wave's propagation. This movement is key to understanding wave behavior in physics. Now, let's look at this diagram 14.6. It shows a harmonic wave moving to the right along the x-axis at different times. Let's look at this diagram, figure 14.6. It shows a harmonic wave moving to the right along the x-axis. Along x-axis. The shape of the wave stays the same, but its position shifts to the right as time goes. Look at here. Position shifts towards the right. This is a classic example of wave progression, where the disturbance travels through the medium, carrying energy forward. So, in A, this one, and in B, one is B. Clear? The shape of the wave stays the same, but its position shifts to the right as time goes. So, in B, the position is this one, and C, the position is this one, and D position is this one, and E position is it shifts towards the right. So each part of the diagram labeled from A to E represents the wave at a slightly later moment. Clear? So wave patterns moves to the right, showing the direction of the wave travel. And this helps us visualize that the wave is not standing still, it's actually moving through space over time. Now we will understand the what amplitude means in the context of waves. So let's look at the displacement relation for a sinusoidal wave moving in the position x direction. The formula is y of xt is equal to a sine kx minus omega t plus phi. Here y is the displacement at position x and time t. A is the amplitude, k is the wave number, omega is the angular frequency. Clear? So from the above expression, since the sine function varies between 1 and minus 1, displacement y of xt varies between a and minus a. So now let's define amplitude more clearly. Amplitude is the maximum displacement of any point on the wave from the equilibrium position. In our equation, it's represented by small a. You can see figure, this one, figure amplitude of a progressive wave. That amplitude is the height of the center line from equilibrium position. This one is the amplitude. Clear? Height from the center line, or we can say equilibrium, to the peak of the wave. So peak of the wave is this, and this one is the amplitude. So it's important to note that while the displacement y can be positive or negative depending on the position and time, the amplitude a is always a positive value. Amplitude only tells us how far the wave moves from the center, not the direction. Now, understand the phase of a wave. Phase, it describes the states of motion of a wave. In other words, it tells us exactly where the wave is in its cycle, whether it's at a crest, trough, or somewhere in between. So, in the displacement equation of wave, y of xt is equal to a sine kx minus omega t plus phi. This is a standard equation. So, term kx minus omega t plus phi represents phase of the wave. Clear? This entire expression is called the phase. The phase tells us how far along its cycle the wave is at any position x and time t, where k is wave number which is related to the wavelength lambda by k is equal to 2 pi by lambda. Omega angular frequency related to the period t by omega equal to 2 pi by t. This formula uh, omega equal to 2 pi by t is very important. Phi is initial phase, which is the initial position of the wave at x equal to 0 and t equal to 0. Phase is measured in radians, which is the standard unit for angles in physics. Now, uh, let's look at the symbol phi, written as this one, phi. Clear? So, this represents the initial phase angle of the wave when time t equals to 0. In other words, phi tells us where the wave starts on its cycle at the very beginning. For example, if phi is 0, the wave starts from 0 displacement. And if phi is 90 degrees or pi by 2 radians, it starts from its maximum value. It's possible to set phi equal to 0 by appropriately choosing the origin on the x-axis and the initial time. So, dropping phi here or set it to 0 in the wave equation, the general displacement equation for the wave is y of x t is equal to a sine kx minus omega t plus phi, where a is the amplitude, k is the wave number, omega is the angular frequency, phi is the initial phase. So, displacement of the wave can be written as y of x t is equal to a sine kx minus omega t. This is the standard form. Example: a progressive wave is represented by the equation y of x t is equal to 0.05 sine 100 pi t minus 2 pi x, where x and y in meters and t in seconds. Find the wave's amplitude, frequency, and wavelength. All right. Let's see the solution. General wave equation is y of x t is equal to 0.05 sine 100 pi t minus 2 pi x. General expression for a progressive wave traveling in the position x direction is y of x t is equal to a sine omega t minus kx. Let's compare the given equation to the general form. First, let's find the amplitude. So, amplitude A is A equal to 0.05 meter. Angular frequency omega equal to 100 pi. Wave number k equal to 2 pi. When we compare this equation and this equation, so A is this one, omega 100 pi, clear, and x is here this one, k is 2 pi. When we compare k x, so k equal to 2 pi. All right. By comparing the coefficient of t, we have omega equal to 100 pi radian per second. Using omega equal to 2 pi f, the frequency is f is equal to omega upon 2 pi. So let's substitute the values. So f equal to 100 pi divided by 2 pi. So after simplifying, we get f equal to 50 hertz. This means the wave completes 50 cycles every second. Now, By comparing the coefficient of x, we have k equal to 2 pi meter inverse. So to calculate the wavelength lambda using k equal to 2 pi by lambda, so lambda equal to 2 pi by k. So substitute the value of k, so it will be lambda equal to 2 pi by 2 pi. So lambda equal to 1 meter. Let's summarize what we have studied so far in this lecture. A progressive wave can be mathematically represented as y of xt is equal to f of x plus minus vt. X minus vt indicates wave motion in positive x direction and x plus vt indicates motion in negative x direction. For a sinusoidal wave traveling in positive x direction, the displacement equation is y of xt is equal to a sine kx minus omega t plus phi, where a is the amplitude, k is the wave number, omega is angular frequency, and phi is initial phase angle. Amplitude A represents the maximum displacement of particles from their equilibrium position. Phase kx minus omega t plus phi describes the wave states of motion at any point and time. Phase is measured in radians. Phi representing the initial phase angle where x is equal to 0 and t equal to 0. Let, now we have some practice questions. First, a progressive wave is represented by the equation y of xt is equal to 4 sine 2x minus 60, where x is in meters and t in seconds. What is amplitude of the wave? Second, calculate angular frequency omega of a wave equation y of xt is equal to 4 sine 2x minus 60. The equation of a wave is y of xt is equal to 5 sine pi x plus 2 pi t plus pi by 4. Is this wave traveling in the positive or negative x direction? 4. For a wave equation, y of xt is equal to 3 sine 4x minus 8t plus pi by 6, find initial phase angle. Fifth, find the wave's amplitude, frequency, and wavelength for a given progressive wave. Y of xt is equal to 0.05 sine 100 pi t minus 2 pi x, where x and y are in meters and t is in seconds. Clear? Thank you for your attention. I hope this lesson was helpful.